Good evening all, I'm Milinda Yapa and I'll be presenting our experimental studies on the permanent shape change of thin-ply composites. First, I will briefly go over the outline of the presentation. I will introduce the applications of thin-ply composites and how they motivate to carry out the study. And after setting up the objectives, I will discuss our experimental work, which consists of tensile tests on a thermoset epoxy to determine the yield point and the plastic strains. And this epoxy is the matrix for the composite that we are studying. And then we move on to the bending tests on the thin-ply composite and the measurements of residual curvatures, and then the conclusions and the way forward. Thin-ply composites have gained recognition in aerospace applications, for example, deployable booms used in solar sails. These deployable booms act as critical structural support to the solar sail during deployment as well as in the post-deployed configuration. With strict mass and volume limitations on the satellite, thin-ply composites are ideal candidates to addressing these limitations due to their low weight and the ability to conform to high curvatures, which increases the packing efficiency. In more recent developments to use the thin-ply composites is the Advanced Composite-Based Solar Sail System developed by the NASA Langley Research Center. The composite booms in the solar sail are about 7 meters long, and the booms are first flattened and rolled in spools for stowage until deployment. Booms store strain energy during folding, which is released during unfolding to assist the deployment of the solar sail and to achieve a final shape accuracy of the boom and its cross-section. But due to the viscoelastic effects and possible yielding and damage in the polymer matrix, there can be residual deformations at the time of deployment. Although any residual strains due to viscoelasticity are recoverable, the deformations due to yield and damage are permanent. In our work here, we have studied the permanent deformation of both the matrix, PMTF7 in this case, and the composite, fabricated with PMTF7 epoxy and F30S fiber. Due to the behavior of PMTF7 and the composite during loading, the best method to identify yield or permanent deformation is checking for irreversible deformation after a certain recovery period. This sets our objectives. First one would be to determine the onset of plasticity or yield point of PMTF7 under tensile loading. And then we move on to the thin-ply composite and determine the onset of permanent deformation under bending, which can be due to yield or damage. First, we carried out tensile tests to determine the yield point of PMTF7 epoxy. On the right here is one of the specimens prepared with strain gauges. Each test was performed having a loading, a relaxation, and a recovery period. The recovery period is to allow the samples to recover of any viscoelastic effects. Initial tensile tests were performed on 3 different specimens at 3 different strain levels. After recovery, the samples stretched to strain levels of 1.05% and 1.35% showed residual strains less than 0.01%, which were below the uncertainty measurements of the strain gauges. So they were regarded to have fully recovered. The specimen stretched to a strain of 1.73% showed a permanent residual strain of 0.03%. To solidify that yield has occurred, 2 additional tests were conducted on the specimen that reached 1.73% strain. On second and third cycles, strain levels of 1.67% and 1.75% were imposed. The figure shows the engineering strain versus time during all the periods of loading, relaxation, unloading, and recovery. And if we look at the recovery portion from bottom up, it can be seen that the permanent residual strain has increased consistently with each cycle. The 3 figures show the strain measurements during recovery together with the temperature measurements. It was seen that any variation in strain can be accounted with fluctuations of temperature. When looking at the permanent residual strains after recovery, the residual strain has increased from 0.03% to 0.045% at the end of the second cycle and subsequently to 0.062% after the third cycle. So now it can be concluded that the yield point should reside between 1.35% strain and 1.67% strain, but it should be closer to the latter. Now let's move on to the bending tests on the thin-ply composites. For the study, a 45-degree oriented 3-ply plane weave laminate is used. The laminates were bent to the desired curvatures by using the column bending test. Two sets of tests were conducted. Set 1, the coupons were bent to desired curvatures at room temperature without a relaxation component. For the set 2, using the same curvatures but at 70 degrees Celsius with a relaxation component of 2.5 hours. 5 coupons were tested under 5 different curvatures, and the figures on the right gives a visual understanding of the range of the curvatures used. The two figures show the moment curvature relationship for the two sets of tests conducted. For all cases, the loading stage is linear, and the depletion of moment during unloading can be accounted to viscoelastic effects. The reduction of the moment at the specified final curvatures of the tests performed at 70 degrees Celsius is due to the relaxation period. The figures here show the deformed shape of the coupons tested with relaxation at 70 degrees Celsius after recovery. It can be seen that as the initial curvature increases, the permanent residual curvature also increases. The recovered coupons were examined with the DIC system. On the left is one of the samples prepared for the measurements. The paint is applied on the tension side of the sample, and the blue lines mark the gauge length. The deformed shape, with the spatial coordinates as analyzed by the DIC, is displayed in the image on the right. During the tests, bending is performed along the y-axis, and since the laminates tested are 45-oriented plane wave, bending coupling is significant. The DIC measurements have been able to capture the transverse curvature in the x direction in the deformed shape as well. The two figures show the distribution of curvatures in the y direction for the two of the samples tested with the relaxation component at 70 degrees Celsius. The residual curvature for each sample was calculated by taking the average over the area. The figure shows the data on residual curvatures versus the initial curvatures. Here the initial curvatures are those imposed on the samples during the test. The blue markers indicate the tests that were conducted at room temperature without the relaxation component, and the red markers indicate those run at 70 degrees Celsius with the relaxation component. From the plot, it can be seen that there is a significant increase in residual curvature compared between the two tests. It should be noted that at 0.05 per millimeter initial curvature, the test run at room temperature shows no permanent deformation. This indicates that the onset of permanent deformation is between 0.05 and 0.1 per millimeter initial curvatures at room temperature. But once the temperature is increased with the addition of a relaxation component, now suddenly we have a permanent deformation at 0.05. So the onset point of permanent deformation must have changed. It should be lower than 0.05 per millimeter curvatures for the test run at 70 degrees Celsius with the relaxation component. So two things have changed from the room temperature tests. One is the increase of temperature, and the other is the addition of the relaxation part. So this could be an effect from either one of them or both of them. To differentiate this, a single test at 70 degrees Celsius was conducted without the relaxation component, and the data is depicted with a black marker. And it can be seen that it's very close to the test run at room temperature than it is to the test run at 70 degrees Celsius. This means that during relaxation, more residual curvature is accumulated. This is only one test here, but considering the difference between the values, it is quite possible that this is the case. Then it would also imply that the duration of relaxation will also affect the permanent deformation. The relaxation duration is 2.5 hours for these tests conducted here, and if the duration is further increased, the residual curvatures will possibly increase as well, although more tests need to be conducted to confirm this. To conclude everything, from the tests run for the PMTF7 epoxy, we have determined the yield point of the epoxy to lie between 1.35% strain and 1.67% strain. And from the composite tests, the residual curvature increased significantly with the increase of temperature and the addition of a relaxation period. But it was discovered that the increase can be accounted for the relaxation period. Moving forward, we would conduct more tests at 70 degrees Celsius without the relaxation component, because we only had one test for that, and also conduct more tests by changing the relaxation duration. And finally, I would like to acknowledge the NASA for their financial support and the NASA Langley Research Center for providing the composite specimens and the test fixtures. Thank you, everyone.